So now for what concerns the models, today we will use the blackboard, and we will use this document, which is the original document of Credit Suisse regarding Credit Risk Plus. You find the document on Blackboard. It's a very nice document, actually, because we will cover together essentially the appendix, Appendix A, where you have the complete description of the complete. What they want to disclose about the model, it's in the appendix. And we will cover essentially the entire Appendix A. Appendix B and C are not relevant for us. And essentially for the exam, this is what you have to know, okay? I strongly suggest you, not for the exam, but if you are interested in this kind of stuff, also to have a look at the chapters. They are very short, so in total, how many pages? Yeah. If you remove all the tables, it's less than 50 pages. And a lot of graphs, so it's even less. And the chapters are very nice also as an overview of credit risk as a whole. So you have a very nice, if you want, summary also of Basel II, because they were discussing, not yet implemented because 1997, but they were already discussing something. And yeah, I think it's a very nice document. So what we will do now, essentially, we want to build Credit Risk Plus. Credit Risk Plus, as I told you, it's a reduced form model. That is to say that you have the defaults of companies are the probability of default, and so obviously the default of companies are IAD conditionally on some common economic factors. It's a Poisson mixture because these probabilities will be Poisson, and that's the difference from Bernoulli. But we will exactly follow the way in which the guys of Credit Suisse have produced the model. And you will see it's a very constructive way, which I think it's very interesting, because we will start with some implausible assumptions, for example, independence, and not conditional independence, independence. So they are all independent. And then we will start removing that assumptions, complicating the model. But then the idea is that if you start with independence, you already have the toy part of the model, and then you just implement the different characteristics. So what we will start with is essentially Credit Risk Plus with independent defaults. The idea is that you have a portfolio and all the obligors are independent, okay? And each obligor will have a probability of defaulting, and this probability of defaulting is assumed to be constant over time, okay? So we will start with Credit Risk Plus with independence and fixed rates of default, or if you want, fixed probability of default. That will be the first step. The second step will be to remove the idea that probability of defaults are fixed, but they vary over time, because obviously what you typically observe in basic models is that, okay, you have fixed one year time horizon, and I assume that more or less the probability of default over this time horizon is constant. The typical example is credit metrics, okay? You have credit ratings for 1 year. So until you do not update the credit ratings, the probability is essentially given by the threshold, and the threshold is there. Here we will remove, so we will have variable default rates. That will be the second step. Obviously here is always credit risk. And the last step will be to assume that defaults are not independent. So we will start model dependence. And here you will see the complete model in which you have the conditional independence, okay? Obviously, this is how we build the model. Today, essentially, we will arrive here. We will consider the model in the unitemporal framework, that is to say over 1 year, but then the model can be extended on the multi-temporal framework, more years. And so here you have t greater than 1, and the same here, t greater than 1. Okay, so the model is multivariate since the beginning, even if here it's very simple because it's just multiplication of the marginals. But it's already multivariate, it's already a portfolio. We can extend to multi-periods, and the same for all the different versions of the model. Okay, so it's also, if you want, from a pedagogical point of view, it's a nice model, because here you will see that it essentially is not yet a real Poisson mixture. It's faking a Poisson mixture using a Bernoulli mixture, but you will see in a minute. Okay, so we start, and the idea is that we have a portfolio. So we have one portfolio. With n obligors. Okay, so we have n obligors. So this is the starting point. Then we assume that for each obligor, we know the default rate over 1 year. Okay, so with pi, we indicate the default rate, as they call it. I don't like this because for me a default rate is something different, as we will see with credit default swap. Let's call as they do. It's a probability of default. So it's the default rate of obligor I, that obviously can go from 1 to capital N, over 1 year. And what is important is that is fixed. So the idea is that fixed does not mean that it's the same for all obligors. That means that for that obligor will not change over 1 year. That's it. And then can be different for all the obligors. Okay. Now, why I told you that we are essentially cheating when we speak about a Poisson mixture, because we will start considering default as a Boolean event. So you either observe default or you do not observe default. So it's 0, 1, it's Bernoulli. Okay? That if you want, if you remember what we told last time, you can always transform a Poisson mixture into a Bernoulli mixture, just taking the indicator that you observe at least one default. So for us, in the very beginning, a default is just either 0 or 1. And even if you consider the case of Poisson default, so in which the same company can default more than once, and obviously you have the shareholders bringing back capital and so on, what do you have? You have the default are discrete. You know, it's not a continuous quantity, it's a discrete quantity. So we will just play with probability mass functions, okay, not with densities. So what we introduce now is a special representation of probability mass functions using probability generating functions. So what we introduce is the quantity GIZ, where Z is an auxiliary variable, and what is GIZ? GIZ is the power series representation of the probability mass function of the defaults of obligor I. Okay, so don't I repeat, I'm not writing it, otherwise it's the rest of the class. GIZ is the power series representation, because that you will see is the probability generating function of what? Of the probability mass function of the number of defaults of our counterparty I. Then we will see that this representation for the moment is a little bit stupid, but you will see in a moment. So how we define that is the summation from 0 to infinity of the probability of observing n defaults for I. Let's write this in this way. So it's the probability of observing n defaults for obligor I, okay? And here you have the power series representation. Okay, this object and probability, if this is the probability mass function, so can be Bernoulli, can be binomial, can be Poisson, discrete in any case. If this is the probability mass function, this object in general, this guy, it's called probability generating function. And for certain purposes, especially if you want to make an analysis of probabilities from a combinatorial point of view, it's very powerful. Because then what you have a polynomial in Z, which is an auxiliary variable, so essentially you don't care, and these will be the coefficients. And the coefficients are given by the probability mass function. So if you are able to extract the coefficient from your series, essentially you have the probability mass function of a random variable, which is very nice. Now, this is very, very, very general. Okay, this is just the definition of probability generating function. Now, let's essentially transform this to our case. We say that for us, a default is something that we observe or we do not observe. So, how many states of the word do we have? 2, 0, 1. Okay? Because more than 1 makes no sense. It's always a default for us for the moment. So this guy essentially reduces, is no longer a summation to plus infinity. It will be the summation for n equal to 0. I observe 0 defaults. And n equal to 1. I observe 1 default. And that will essentially take all the rest of the word. 2, 3, 4, 5. I don't care. Okay? So what's the case for n equal to 0? This guy is z to the power of 0, so it's 1. What is the probability of not observing a default? It's 1 minus pi, 1 minus pi, okay? This is the first term. And then we have the second term. What is the probability of observing 1 default? It's pi, z. Okay? If you want, you can rearrange, just take p. So this is 1 plus pi that multiplies z minus 1. Okay, it's not a big surprise. This is the probability generating function of a Bernoulli. Okay? Just cheating, we knew that, but nevertheless, now we, sorry, we have it. So we start, so what we have, I will write it here because maybe later we use it. I just copied that. Okay, this is the probability mass function of my single obligor. Now, I'm considering n obligors, so I'm considering a portfolio. What I'm interested in is the number of defaults in the portfolio. But what I'm assuming from the very beginning that the n obligors, I told you, is not written here, but it's all independent, okay? they are independent. So you can imagine, what do we know about the probability of having k defaults in the portfolio? Will be essentially given, the joint will be essentially given by the product of the marginals. And the same, it's true for the probability generating functions. So I can introduce g of z without I to be essentially the probability generating function of the whole portfolio. Okay? Because of independence, it will be essentially the product for 1 to capital N of GIZ, is to say the product for 1 to capital N 1 plus pi z minus 1. Okay? And this is what we know about the probability generating function of the entire portfolio. Now, one thing that we can do is the following. Let's take the log on both sides. Okay? So we take the log. And here we have the logarithm of g of z. Okay? And here what do we have? We have the sum of the logs of this. Okay? So it will be the sum from 1 to n of log of 1 plus pi z minus 1. Now, what can we observe is the following. I told you that there are classes, and we know from the transition metrics that we have seen when dealing with credit ratings, there are classes like the CCC in which the probability of default is not so small. It's 20%, more or less, 19, and blah, blah, blah. So it's not a small probability of default. But for the moment, do not consider that. Assume that you have a very nice portfolio with AAA, AA companies. So what do you know? You know that the probability of default of your counterparty, then we will correct for that. But for the moment, no. We are in the simplistic approach. What we know is that PI will be small. It will be an extreme event, if you want. But if this is true, this term here, if you remember an approximation that we have seen also in extreme value theory, when x, so if you have the log of 1 plus x when x is tending to 0, and this is essentially the case here when this is very, very small, this guy is approximately what? This guy here is essentially pi z minus 1. Since pi is small, okay? So if you want, just write that for the moment we are assuming that we have companies whose probability of default is small. So that means in practice that we are not considering CCC, CC, C companies. They are very all reliable, more or less, companies. So what we have is now we have the sum, more or less, this is approximately the sum from 1 to n of pi z minus 1. Okay? Okay. Go back. So exponentiate on both sides. Exponential, yeah, probably says exponentiate, I don't know. Essentially, you revert, you want g of z, and so what do you have? G of z will be e to the power, the summation in pi of z minus 1. Okay? So from 1 to capital N. If I call the summation of my pi mu, okay, sorry, pi, this guy reduces to this, okay? What are the PIs? So what is PI? For every obligor I, PI is the probability of default, okay? And this is a Bernoulli variable. And for a Bernoulli, this is also what? The expected value, okay? It's the expected value of the indicator. So what's mu? It's the expected number of defaults in our portfolio. This is expected number of defaults in our portfolio. So this is what we have. Okay, may I delete here? This part, if you want, it can also be boring in the sense that it's trivial. These derivations is trivial. But I think it's very nice because then when you go back with a more advanced model, you will see that you just substitute this, just substitute that, and the rest of the model is heuristically preserved. So we have here, let's write now that Gz is equal to e to the summation of pi z minus 1 or e mu z minus 1, okay? This is what we just write here because later we will use it. Now, consider this absurd transformation. Okay? Now, what we can do, let's give the series representation of the exponential. Okay, here. So what do we have? We have e to the minus mu here, and nothing for the moment changes for us. And here we have for n from 0 to plus infinity, what do we have? We essentially have n factorial here, okay? And then at the numerator, we have mu to the power n, z to the power n. Okay, now take this part, e to the minus mu, and put it down, inside the summation. So this is the summation for n from 0 to plus infinity of e to the minus mu, mu n factorial zn. You agree? This is, if you want, the summation from 0 to plus infinity of, let's call this object, I don't know, an zn. What is this? Yeah, exactly. It's the probability mass function of a Poisson. And this is the power series representation. So it's the probability generating function of our portfolio, which is Poisson. So this is a Poisson. Of parameter, or well, I don't know if you want to be English or American. Yeah. Which is the expected number of defaults. What do we know now? Let's say that X is the number of defaults in the portfolio, okay? And this is our portfolio. What is the expected value of X? If it's Poisson, what is that? And what's the variance? Yeah. Wait. I know you will never do that, but better be safe. Because if I write var, then I have people saying it's valid risk, because we are in credit risk and they forget about the variance. Yeah. You laugh, but you have credit risk managers. I was once, I told that every time because once I was in a quite important bank speaking about value at risk, and after 40 minutes, the risk manager said, yeah, but why are you so interested about variance? Yeah, okay. And that was my bank at that time. After 1 week, I moved my bank account to another place. So it's also the variance. So what do we know if you take the standard deviation? It's the square root of mu, okay? Now, why this digression? Who cares? Because who cares is essentially this point that looks like a silly thing is essentially one of the points in which later Credit Suisse, so the guys in Credit Suisse, intervened to modify the model. Why? Because if you go in data, so you consider empirical data, and you assume that your mu is correct, so that the number of defaults in your model is okay. If your model is this model, that will be the standard deviation of the number of defaults. But empirical analysis show that this number is much larger than this. So the standard deviation of defaults is larger than the square root of mu. If your mu is correct empirically, what you would expect from a theoretical point of view is that the standard deviation is square root of mu. Empirically, it's larger. So that means that there is something in this model that does not work. And that's why, for example, the first step will be, okay, we will see as a first step moving to the multi-period, but conceptually there is no difference. The real first modification is to introduce variable default rates, variable probability of defaults. The idea is that we will fix the time horizon, because we need to fix the time horizon, because we want to make our assessment with respect to a time horizon, but we will let the default rate vary within this time horizon. Okay, it's no longer fixed, can vary during the period. Okay. It's clear until now? Now, what you have to remember, because that will be what we will use, is that if we start with our independence assumptions and blah, 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 we have our PIs, we have Bernoulli default here, and Poisson for the portfolio, okay? And we have derived that analytically. Now, the point is that with a trick, which is very common in actuarial mathematics, we will transform a little bit our data. Because what do we know about our portfolio? For the moment, we have just introduced the number of obligors, and we have said that these obligors are independent. We know that they have different PIs, and that they are fixed over the time horizon. But you can imagine that every obligor, if we are interested in assessing credit risk, will have an exposure. Okay? So the amount of money that, in principle, we may lose in case of default of the obligor, and that will not be the same for all obligors. We will play on this quantity, because what we can introduce now is the quantity EI, which is the exposure of I. The exposure of I is, I don't know, 20,000 euros for I equal to 1, and for I equal to 10 is 2,000 euros, for another guys is 1 million euros, okay? So these are essentially the very potential loss. Why just potential? Because you know that you have recovery rates, so actually what you lose is less that, but this is the upper bound. You cannot lose more than that. Now, let's introduce a quantity E without any subscript. That will be our unit of computation, or if you want to be fancier in financial mathematics terms, the numéraire. Which is the French way of saying the same stuff. So E will be the numéraire. What does it mean? It means that it will be the quantity with respect to which all the other quantities are defined. Simple example. Assume that EI is 12,500 euros, okay? And let's say that E is 1,000 euros. That's it. This is what we are doing. Which is something quite trivial, but you will see it's important, because that will be the way in which we can consider these quantities, in principle, the exposure of your counterparty. In principle, it's a continuous quantity, okay? You can assume all the values from 0 to, I don't know, the money your bank has, okay? I can assume all these values in principle, because in practice it's not true. You always have numeraires that you apply. Even if you get 22.27 euros, it's just because it's the multiple of some unit that they have defined. But in principle, these are continuous. If you use the numeraire, you will see it's the first trick to discretize these quantities, because this is the first step, and then we will have a second step. So what we have, consider this example. Let me call this quantity nu I. So nu I E, or it's very nice in the report, because in the report you see that it's really, so it's not the guys here, but since they have to sell this stuff, it's really credit risk plus for dummies. And so you also see this. It's very nice. Yeah, but okay, so it's stupid, but it's full of this kind of stuff. And if you know something about consulting, you understand why. Because otherwise, yeah. Okay. So this is the nu I. So what is nu I for us? Nu I will be essentially the exposure in terms of numeraire. Okay, it's the multiple of the numeraire. So it's the exposure in terms of E. So in that case is simple. We will have a little bit more later. And whereas, yeah, the last quantity, and then I think we stop for the break. Another quantity that today we will not use a lot, but next time, yes, it's a quantity which is lambda I, which is defined always in terms of the numeraire, but this time you have epsilon I E, and this is essentially the expected loss. So what's the difference? This is the exposure. This is the expected loss. So these guys will be always something small. It's smaller than equal to the exposure, because you cannot lose more than the exposure. And it's exactly the guy that takes into consideration the recovery rate and blah, blah, blah. Okay? So it's essentially, if you want, is the loss given default, not in as a percentage, which is the typical, is the nominal loss given default. Okay? And these are the quantities that we need, and we continue after the break. Okay, so we have introduced these quantities, the exposure, nu I, which is essentially the exposure in terms of the numeraire, and then we have the expected loss. Now, consider this example again, okay? Let me just... Here we have said that if E is equal to 1,000, okay, nu I is equal to 12.5, okay? Now, what happens if E is 10,000? This will be 1.25, okay? Now, assume that we take this quantity and we round this quantity to the closest integer. If our E is 1,000, the closest integer here is 13, okay? If I use E 10,000, the closest integer will be 1, okay? Now, what's the point of this? The idea is that, essentially, if I have all my exposures of counterparties, I will have a collection of EI for I from 1 to n, and this will generate a collection of nu I that is just this in terms of the numeraire, from 1 to n. But now, if I choose the numeraire in a clever way, I can define bounds such that when I round this quantity to the nearest integer, I will have the different exposure falling in one of these bounds. So I can define bounds or they call that classes, bands, and so on, such that I can essentially further discretize this quantity. How? Imagine that my numeraire is 10,000, okay? One bound can be the bound that goes from 1 to 2. All companies that are between 1 and 2 will be in that bound. Okay? So I can choose the numeraire in a clever way, which is not the easy part, actually. But what you will have is that you can have your exposures, your counterparties, divided into m bands of exposures, given this rounding. Okay? So the idea is that I can now define, in terms of my J, nu J, which is the common exposure in terms of the numeraire of all counterparties falling in class J. Common exposure in class J. So I repeat, let's take an example. Consider nu 1, nu 2, nu 3, and nu 4. These are my exposures for 4 counterparties. And let's say that in terms of E, which I don't care, it's 1.25 E, 2.3 E, 7 E, and 0.9 E. Okay, these are my exposures. Now I round to the closest integer. Okay, and this becomes 1, this becomes 2, this is 7, and this is 1. Okay, I'm just rounding. What?
Just by definition, the nu is not 1.25 E, right? Because that's the EI.
So this is nu I.
Yeah.
Ah, yeah, sorry, yeah, sorry. Yeah, you're right. Yeah, sorry, yeah. Yeah, you're right. Sorry. Yeah, these are the EI, sorry. E1, E2, E3, E4, yes. So this is nu 1, nu 2, and so on. Okay? Yeah, thank you. So what you have is that now I have 1, 2, 7, 1. So if you want, I have aggregated these two in class J equal to 1. This will go in class J equal to 2, and this will go in class J equal to 7. Okay? And I can do this for all my counterparties. You can imagine that number of classes will change depending on E, on the numeraire. If it's very small, I will have a lot of classes. It's very large, I can have everything in one class. Okay? More or less. Now, the idea is how to calibrate these, which is the tricky part. You find the reading there. So I'm not saying it's in the appendix. So I think it's just one short paragraph. Obviously, they don't give you all the tricks, but they give you some insight. So what I can do, essentially, I can make this transformation. Now, this transformation, as you can imagine, will introduce some approximation error in the loss distribution, okay? Because we are rounding. The point is that first we are playing with random quantities, and so 10 euros more, 10 euros less, this is not a big problem. But even 10,000 euros more, 10,000 euros less for a big bank is not a big problem. This could be the first justification. And the second is that if you play correctly with this, you can really control for the approximation error. More or less, you can even compute it, and you find something in the appendix there. Okay, so we don't care about this problem for the moment. We have induced this transformation. Now, what will happen? We are taking our companies, okay? So here I have my companies, 1, 2, 3, 4, 5, 6, 7, and I'm just putting these companies in groups, okay? Like this. This is what I'm doing. I'm just aggregating my companies. Now, the trick will be to consider each of these groups as a portfolio, as a sub-portfolio containing these companies. And I will assume these portfolios to be independent, which is not even an assumption. It's something that you obtain from your original assumptions, because we are assuming that these guys are independent from the very beginning, okay? If these guys are independent, once I choose E, the J's will be independent, okay? And when I put them in the different classes, within the classes I will have the independence. So I will have M, because J is going from M to M, and independent sub-portfolios. And this will be one of the tricks we will use. But before introducing that, we introduce some further, it's always the same, but now, nu J is the common exposure in class J. Common is the average exposure in class J, okay? So they say common, but because common means anything from a statistical point of view, it's the average exposure in class J. So nu J is that. Then we have epsilon J is the expected loss in class J. And with mu J, we indicate the expected number of defaults in class J. Okay? Now, if this is the expected loss in class J, this is the common exposure, and this is the number of defaults, which is the relationship among them. This is equal to the expected loss in the class will be the common exposure multiplied by the expected number of defaults. Okay? So on average, I lose 1,000 euros per obligor. In that class, I have 10 defaults, 10,000 euros. Okay? I will then let you, I will not tell you why, but I will let you then think about that for the entire weekend. If this is true, then mu J is equal to this, okay? And if you want, yeah, you can prove it. Okay, so Now this is stupid, but there is another thing which is still simple, but it's nice to take into consideration. Okay, we agree on this. Okay, we agree on that. Now, this will be, remember that this is the average exposure there. So what is this? This is equal to the sum for the I, for the I in class J, okay? It's horrible the way to write it. It's for the I in class J of what? Of epsilon I mu I. And this is something that we will use. So we take the i's that fall in our class J, in our band J, and this is something we know. We will use that essentially in the more complicated version of the model when you have variable rates. But since we are making something constructive, we use it. Now, come back to this, okay? Remember that we are always dealing with the same portfolio. It's always the same. Now we have just added some extra notation in terms of exposure, okay? But now, what do we have? From these, are there questions? From these, what we have said, what do we know about the expected number of defaults? Is mu, okay? Now then you agree with me that if I know this, necessarily mu is equal to the sum for j from 1 to m of mu j. Okay? And obviously you can also copy the rest. So is equal to this guy, the sum of these guys, and then the double sum of these. Okay, let's introduce another probability generating function. So for the moment we have considered two probability generating functions. One is the one is the one of the single obligor, and one is the one of the portfolio in terms of number of defaults. Okay? What we are now essentially needing is the probability generating function of the losses. We are interested in the losses because at the end of the day, we will need a loss distribution on which we compute the var and whatever you want. So we have to compute a loss distribution. We call this L, okay? With the usual notation, it's L of Z instead of G of Z. And L of Z for us is what? It's essentially the sum for n from 0 to infinity of the probability, then the aggregate loss in the portfolio. Okay, otherwise I just write with my nails. Oh. So the aggregate loss is what? Is n times E. So I define the aggregate loss in terms of the numeraire. Zn. Okay? It's the usual thing. This is the object I want to compute. Okay? Now, remember what I told you. N obligors independent. If the n obligors are independent and you apply all the transformation we have seen with approximating the exposures of the obligors, I will have that the m classes are independent. But then if this is true, I will have that my loss distribution over the whole portfolio will be the product of the loss distribution on the sub-portfolios represented by the classes. Okay, so that will be the product for J from 1 to M, the number of classes I have, of LJZ. Now the trick is to replicate exactly all the things we have done before for the entire portfolio for the sub-portfolios. Why? Because we have independent classes and we will use that here. But even within the classes, we will have essentially the independence, or if you want to relax, even the exchangeability, but nothing will change. So what we have is that I just copied that here. I have that my LZ is equal to the product over the J of LJZ. And here, remember that mu is the summation over J of mu J. And now, what I will do is to see what LJ looks like. Okay? Now, in the appendix, you find more details. I'm just jumping over that because it's exactly the same construction we have seen so far. So what you can see is that LJZ, if you have that each sub-portfolio is mimicking the big portfolio, essentially what you get is that LJZ is this object is equal to the sum for M, from 0 to infinity of the probability of having n defaults, Zn mu j. And these, using the consideration we have seen before, is essentially the sum of what? Of e to the minus mu j to the power of n, and the denominator n factorial, and here you have Zn mu j. So it's just an adaptation of what we have seen so far. And this quantity is equal to what? Is equal to e to the minus mu j, okay? Plus, on the other side, mu j, z mu j. And you recover what we have seen before apart from the j's. Now, if this is Lj, my Lz will be the product over j from 1 to m of the LJs. Okay? Take the product of these guys, and here you will have e to the minus the sum over j of mu j, okay, plus the sum over j of mu j z mu j. This guy, if you want, you can substitute mu. And okay, but it's totally irrelevant. So what we have is now the loss distribution of the portfolio, in which there is always the Poisson component, because remember that here you can again make the transformation in the power series and you will find the same consideration. But why is this important? Because this is essentially the starting point of all the rest, especially from a computational point of view. Because you will see that this model, that for the moment is wrong, and we know it's wrong, because it has very strong assumptions like the independence of all the obligors, and which is not at all realistic. We are not saying anything about the approximations. We don't care. It's just to find this relationship that will be the starting point for the real model. And why is this important? Because if there is the Poisson distribution, you remember what I told you last time. The Poisson distribution is in the so-called Pangier class that allows this nice and now I missed the word. Recurrence, thank you. This nice recurrence relation. So I can, the probability of observing k default depends on the probability of observing k minus 1, and so on, until the probability of observing 0 default. And here, obviously, since the losses are expressed as a multiple of the numeraire, it will be essentially the same, okay? Apart from the numeraire is a fixed number, so it's not a problem. Now, I can, and even here, you find a complete derivation is 2 line, but it's it's just boring. And actually, this is the only part I'm not interested in, is the following. There is a very nice way of computing this object, and it's the following. Define an to be what? To be the probability of a loss equal to n times e. Okay, so an is the probability of observing aggregate loss. So this is aggregate at the level of the portfolio, equal to NE. But now, if this is the loss distribution, how can I compute this object? So sorry, if this is not the loss distribution, if this is the probability generating function of the loss distribution, how can I compute this object? I can compute this object in the following way. It's 1 over n, and then I take the nth derivative of what? Of this object. So it's dn Lz dzn, evaluated where? It's like with the moment generating function. The trick is the same, but here we are getting not the moment, but the probability mass function. So where is z evaluated? In 0. Yeah. So when you have the moment generating function, of a random variable, how do you recover the nth moment? You take the nth derivative and you evaluate in 0. That will be the nth moment. For the probability generating function is the same, but the object you get is not the moment, is the probability mass function. So this is what I get. Now if you go here, you find your derivation, which is actually a couple of stuff using Leibniz formula. But apart from that, what you find is that at the end of the day, you can express an in terms of the previous an. So an is the probability of observing an aggregate loss equal to n times e. E does not change, is there. So what we are interested in, n minus 1, n minus 2, n minus 3, up to 0. Okay? I can express this guy in terms of the sum over j, such that mu j is smaller than n. And this is exactly this. Epsilon j over n, a n minus mu j. Look here. I gave you as an exercise, but was totally not compulsory, the distribution. You remember the Pangier recursion? We gave the Pangier recursion just with respect to one leg. So k with respect to k minus 1. But obviously then you can go back. There is one distribution in which the terms a is equal to 0 and the terms b is equal to lambda, and it's the Poisson. It's exactly this one. If you go to the definition of Pangier, there is no fixed term. It's just epsilon j over n, that if you go in the formula we saw, n is r. Okay, in that formula, n is r. So what you see is that this is a recursive formula, and there is obviously an initial condition required, which is a0. And a0 is what? Is L0. L0 means N0, because E is there. Okay, L0, which is E to the minus mu. And this is the essentially the no default case. But consider this object, okay? This object is what? It's this, okay? And this is also equal to the sum in J of what? Epsilon J over mu J, okay? So why is this representation of the loss distribution very useful in practice? If I assume that I am able to define my E properly and all the stuff, consider I have a portfolio of thousands of obligors. If I want to compute the loss distribution of that portfolio using other techniques, other models, can be cumbersome, because I have to take into consideration thousands of objects. Okay? Here, for me, it's just necessary to have information about the J classes. And for a large portfolio, this can be much less information. On historical basis, I have this information, and I can exploit that efficiently. And then I have a very nice recursion that allows me to compute whatever type of loss I want. In this model, it's not really realistic given the assumptions, but you see, it's a nice representation. Now what do we have to do is just to remove the parts we don't like and enter something a little bit more credible. But what is important of this derivation is that the idea is this one, nothing. So you start with one obligor and you show that it's Bernoulli, okay, nothing very special. Then you take the entire portfolio and you show that you have the Poissonianity of the number of defaults. Then you use the trick of splitting the portfolio into sub-portfolio using this discretization, which is very, very common in actuarial mathematics of exposures. When you have, unfortunately, we don't have insurance mathematics in the master because I think it's very nice. But in insurance mathematics, when you have life or non-life insurances, obviously you have the claims come in, and they are always discretized using this technique. Okay, when you make your computation about potential losses, they are always discretized. And you will see later on that this is also related, so the Pangier class and all this kind of stuff essentially emerge from this discretization. That's why out of actuarial mathematics they are not very, very used. And, okay. As home reading, because I'm not covering, but then I will ask at the exam, there are these, 30 lines of reading as a whole. These sections, and then what is, so it's A41, A42, A5, and A6, these sections. Essentially, if I remember, don't remember the titles, but A41 is more details about this, but I'm not really interested in this part. So let's say this is nice to better understand. Then you know that if I say something, then I respect that, but I will not ask you, for example, in the exam to derivate this, okay? But I think it's nice, especially if you are interested to implement. It's something that you have to know if you want later to implement this type of models. And this is essentially the part I also implemented when I was in SAS. And 4.2 is about the precision of the exposure bands, how you can choose them. So it's a nice argument. And then appendix 5, it's the multi-year losses that we will just consider briefly now together, and something about the default uncertainty, default rate uncertainty, which is the starting point to change the idea of having fixed defaults. But it's less than 2 pages of reading. Now, what happens if I want to extend this model, which is uniperiod, multi-period, it's over one period, okay? Actually, in economics will be unintertemporal, but I don't think you use that in financial mathematics. So you have this which is over 1 year horizon, or nevertheless one horizon, 2 years, but it's that. Now, let's say I don't care what is one period, can be 1 month, 2 months, 1 year, but I want to see what happens over more periods, okay? Now, the construction is exactly the same, nothing changes, you just introduce an extra index t, which is time, and essentially you define, obviously you can do that from the very beginning for the single obligors, but then given the aggregations, you will find that at a certain point you will have pjt, that will be the probability of default in the jth class. In period t, you will have the quantities new jt and so on. So you will have all these quantities. there is one thing that is very useful to compute the multi-period extension of what we have seen, and it's the following. It's the defaults for the same company in every period. So a company can default in period 1, but then it's not in period 2. Or can default in period 2, but then it has not defaulted in period 1. So what you have is that defaults over time are mutually exclusive. If you observe a default now, you will not observe the same default next year because that company is out. If you observe the default in 3 years, that means that for the first 2 years, the company was there. So essentially, there was no default in the first and in the second year. They are mutually exclusive. So if you use that, essentially what you can show is that Lj of z is equal to 1 minus from 0 to t of your pjt, and here the summation of a t from 0 to capital T of pjt, and this is z, and here is a mess because it's new jt. So you can give this representation in terms of the probabilities of default, and this representation, essentially all this, the only thing that you have to remember, because defaults are mutually exclusive. If you observe one, you cannot observe the other, so if you want, also their intersection as event is empty. And that's it. This is the way in which you can take, and it's really that's it, because even if you take their document is this part, because all the formulas you have seen are exactly the same. You will have an extra summation over t coming out, and that's it. And this only works because of the mutually exclusivity of defaults. But in that case, it's not an assumption. It's obvious. So this is surely something that we don't have to criticize of even the simplest model. So next time, what we will do is essentially to consider the uncertainty of default rates. So we will allow default rates to change. At a certain point, we will introduce the common economic factors formally. And in Creditrix Plus, the main common economic factor is the industrial sector of the company. So the idea is that we will assume the defaults of companies to be independent conditionally on information about the economic sector. Among economic sectors at the very beginning, we will assume independence, but then also there you can put another layer, which is, for example, the country level or the economy level or whatever level you want. So you will have that the probability of default will be a common part for the entire portfolio, a sector part, and an idiosyncratic part. The idiosyncratic part is independent conditionally on the rest. And what we will introduce is essentially the parameters of our Poisson that are coming here usually will be gamma distributed. Why? Because this is essentially based on empirical analysis. It gives a nice fit. And then the clever trick is that the gamma distribution have some nice properties in terms of moment and how you relate, for example, the first moment and the second moment. You have some very nice closed form that you can include in the Pangaea recursion. And so you just need a few, relatively few data information to make all your computation about very large losses over portfolios. Once you have your loss distribution that you simulate, you apply the value at risk and the formulas of the foundation approach if you're under the foundation, or the other your formulas if you want to use the advanced approach, conditionally on the approval of the regulator. Okay, that's it. If you don't have questions, have a nice weekend.